Okay, so our next derivative is the derivative of log to the base a of x equal to 1 over x ln a, and let's do a proof. So like a lot of these proofs with inverse functions, we start off with a let then statement. That is, if we let y equal log to the base a of x, then this has to be true. A to the power of y would equal x. If y is log to the base a of x, then a to the power of y equals x. It's our definition of a log. Okay, so let's just justify what we're doing. This was just, if this is a proof, I'm saying this is just by definition. And that's how a log is defined. Okay, so here's our goal. Got to have goals. The goal is find the derivative of y with respect to x. Find the derivative of log to the base a of x. Well, we're going to do this kind of we're going to take the derivative over here because we actually know what the derivative of a to the y is. So let's just recall this. We just finished doing it in our warm-up. Recall that if we're taking the derivative of a to the power of x, we get a to the x times the ln of a. So if I'm going to take this, a to the y equals x. So if a to the y is equal to x, and I do the same thing on both sides of the equal sign, that is, I take the derivative with respect to x, then over here on the right-hand side, dx by dx gives me 1. What's the derivative, with respect to x, of a to the y? Well, y is a function of x, so you have a chain rule. This is implicit differentiation. The derivative, if there was an x here, would be a to that power times the ln of a. So this is going to be a to the y times the ln of a. And then I need to multiply this by y prime. Implicit differentiation. So solving for y prime, I get dy by dx, or y prime, is equal to 1 over a to the y times the ln of a. Well, that's not quite where I'm trying to get to. Well, look at what my let then statement said right in the beginning. A to the y is equal to x. So a to the y is equal to x gives me dy by dx is equal to 1 over x ln a. And what's y? Y was log to the base a of x. So the derivative with respect to x for log to the base a of x is 1 over x ln a. So there's the proof for this derivative. I don't expect you to redo that proof, but you do need to be able to remember this definition, or this derivative. Okay, so then the derivative of ln x is just 1 over x. Well, since we just proved this, let's use it to prove this next statement. So ln x, remember ln x by definition is just log to the base e of x. So what's the derivative with respect to x of ln x? It's the same as the derivative with respect to x of log to the base e of x. And look at our derivative definition. This is just 1 over x times the ln of e, which gives me 1 over x. Done. Okay, so a couple quick questions. if I give you y is equal to log to the base 5 of x, what's y prime? Just look back here at your derivative, log to the base a of x, take the derivative 1 over x ln a, where a here is the base. So are you all getting 1 over x ln 5? Anyone want another example like that before we move on? Okay, then try this one. If y is equal to ln x, what's y prime? I guess it couldn't really be easier, could it? It's almost as easy as asking you what's the derivative of e to the x? E to the x. What's the derivative of ln x? 1 over x. Okay, so now we're going to bring in the chain rule, just like you were expecting. Okay, so let's differentiate y equals the ln of x cubed plus 1. So that's y prime. Well, the derivative of ln x is 1 over x, so this is 1 over x cubed plus 1, chain rule times the derivative of the inside function, 3x squared plus 0, which simplifies just to 3x squared over x cubed plus 1. Okay, so you try this. If y is equal to the ln of 2x to the 4th plus 3x, what's y prime? I'll give you a hard one.